Ice is a strange and beautiful thing on our planet. It often looks still and silent. But it is not. Ice can move, flow, and change over time. Snow falls year after year in the coldest places on Earth. Compressed by weight, the air is squeezed out. Snow becomes solid ice. Over millennia, ice sheets grow across Greenland and Antarctica, kilometers thick in places. Some ice forms glaciers that flow across the land. Where a glacier reaches the ocean, it can begin to float. These floating extensions are called ice shelves. Their edges are tall ice cliffs, sometimes called an ice wall. These cliffs can be hundreds of feet high. Ice shelves act like buttresses, slowing the rivers of ice behind them. They are the doorstop that holds a massive force at bay. When the ice wall at the edge fractures, pieces break away. A process called calving. Warming air melts the surface. Warming seas eat the shelf from below. Floating shelf melt is like ice in a glass. It barely changes sea level. But removing the shelf uncorks the glaciers, sending more land ice to the ocean. That new water raises sea level worldwide. We study this ice closely because it is changing, and our future is tied to it. We have watched an ice shelf door break before. In 2002, a large section of the Larsen B ice shelf collapsed. Larsen B lies on a rapidly warming peninsula. In just 35 days, intact ice turned to a shattered mosaic. It did not calve as one piece. It disintegrated into thousands of fragments. About 3,250 square kilometers, some 200 meters thick, vanished from the shelf. The glaciers it buttressed surged forward, some up to 8 times faster. A real-world proof of the buttress effect. Warm summers created melt ponds. Water percolated into fractures, wedging them open, hydrofracturing. Scientists watched astonished as the shelf failed in real time. Larsen B taught us how larger shelves elsewhere might be at risk.
The glaciers are telling us the climate is warming.
It was a wake-up call. Ice can change far faster than we assumed, and when a shelf goes, the consequences ripple outward. What happens if the next great ice wall collapses? Calving is the breaking of ice from a glacier or ice shelf. It can produce single, enormous icebergs, city-sized, or break into countless smaller pieces. Failure starts at weaknesses, cracks, crevasses, and rifts. Surface meltwater pools form as air warms. Water, denser than ice, drives fractures deeper. Beneath, warm currents thin the shelf's base, basal melting. Unpinning at the grounding line reduces stability, like a building losing foundations. Recent decades have warmed both polar air and seas. Together they amplify collapse risk.
Not a good sign when you see a lot of meltwater on an ice shelf.
Cracks can cascade, turning stress into sudden failure. When the wall falls, it can be abrupt and transformative for the coastlines that follow. The question is not if ice will calve, but how fast. Its true danger is in uncorking land ice. The consequences are felt most strongly at our coasts. Floating ice, sea ice and icebergs, barely changes sea level as it melts. It already displaces its own weight in water. But land ice adds new water to the sea. That is what raises sea levels worldwide. Even small rises amplify coastal risk for hundreds of millions. High tides reach farther inland. Storm surges ride on higher seas and become more destructive. Greenland holds 7 meters of potential. West Antarctica, several more. Not a single giant wall falling at once, but processes unfolding over decades to centuries. Some shelves, like at Thwaites, could accelerate loss quickly. Acceleration, nonlinear change, is the greatest concern. Polar life is tied to ice for hunting, breeding, and rest. Under sea ice, algae feed krill, fuel for fish and whales. Lose the ice, and the food web frays. Watching the ice is hard. The poles are remote, dark, windy, and bitterly cold. Satellites map extent and measure height with remarkable precision. Radar sees through clouds and during polar night. They track glacier speeds, showing where ice accelerates. Drones map cracks up close with detail satellites cannot match. Robotic submarines measure temperature and salinity under the shelves. Ocean floats profile the currents that reach the ice. But we still lack full maps of the bedrock beneath kilometers of ice. Seafloor canyons can funnel warm water to grounding lines. Fieldwork is essential and slow, difficult, and expensive. Fracture physics is complex. Why one crack stops and another runs for miles. As Dr. Richard Alley says, the biggest uncertainty in future sea level is the ice sheets and their cliffs. We are progressing, but no perfect prediction for when a great ice wall will fail. So we watch closer, measure better, and narrow the range of possibilities. To navigate uncertainty, scientists build computer models, digital twins of the ice and climate. They simulate how ice forms, flows, melts, and fractures. What if surrounding oceans warm by 2 degrees? By 4? What if we continue current emissions, or cut them quickly? Machine learning combs satellite data for hidden warning signs. New models resolve hydrofracture and sudden cliff collapse. What seems slow can turn fast. Planning must account for acceleration. We do not need to panic, but we must act. Clean energy is scaling, and costs have fallen dramatically. Smarter coasts and restored natural buffers reduce risk. Efficiency and cleaner transport cut emissions now. We have the tools to learn, and the power to change course. If a great ice wall fell, the danger would be the surge of land ice that follows. Coasts stressed, ecosystems strained, and societies tested. The time to act is now.